In this video, we will continue our investigation into the integral test by specifically focusing on the integral test remainder, or we might call it estimation property. And here's a motivating example. How large must n be in order for the nth partial sum s sub n to approximate the given series correct to some degree of accuracy? Here we would say maybe to 3 decimal places of accuracy. Now, let me first remind you of why or how it is we can use the nth partial sum to approximate the series. So we're starting off with a series, and if we suppose that it converges, so if we let S be the sum of the series, that is what we get when we add up all of the terms. The idea is that if we were to stop after adding up just the first n terms, we could use that as an approximation to the sum of the series. We could say S, the true sum, is approximately equal to this S sub n. Now, it's not going to be exact, but what we can do is measure how close it is as an approximation. That is, we can look at the associated error. And if you look at the associated error, if you take the sum S and you subtract away what you get when you add up those first n terms, you're essentially crossing them off, and the remaining terms are going to correspond to your error in approximation. And our question today is really going to be, how small is that error going to be? i.e., can we make it smaller than 0.001? Now, the property we are going to use is referred to as the integral test remainder or estimation property. So if we have a situation where we can apply the integral test, that is, the associated function f is continuous, positive, and decreasing. If that's the case, then this error, e sub n, is bounded above by the integral from n to infinity of the function. And the picture here should hopefully illustrate why that is true. So in the picture, this leftmost rectangle we see will have area a sub n plus 1. The next rectangle over will have area a sub n plus 2. Then a sub n plus 3, and so on. So essentially, if we take all in red, the areas in these rectangles, that would be precisely the e sub n, the error we want to approximate. But if we think about what this integral from n to infinity is calculating, well, in blue you would have all of the area underneath this curve. So the blue area is bigger than the red area. And take that for what it's worth, just a little bit of intuition as to maybe where this formula is coming from. The big thing, though, is can we apply it to solve this problem? So in order to use the integral test estimation property, we first need to, much like the integral test, write down the associated function and verify that the hypotheses are satisfied. So in this case, our function f of x is 1 over x to the 5th. And much like our first example where we had 1 over x cubed, this function on the interval from 1 to infinity is very clearly going to be continuous and positive. And additionally, note that x to the 5th, the denominator, is getting bigger. If you're dividing a constant by something getting bigger, we have a decreasing function. So continuous, positive, decreasing. So what we know is that this error, e sub n, is going to be bounded above by the integral from n to infinity of 1 over x to the 5th. And what we would like to do is determine how large does n need to be in order for that error to be smaller than 0.001. So that is, we want this to eventually be smaller than 0.001. But before we get to the point of dealing with making this smaller than 0.001, we need to evaluate this integral, and then we'll see what we have left. So to evaluate this integral, we first write as a limit. So the limit as a approaches infinity, the integral from n to a, 1 over x to the fifth dx. So noting that 1 over x to the fifth is x to the minus fifth, this would be minus 1 over 4x to the fourth from n to a. So we plug in a, put a minus sign, plug in n. So that would be minus 1 over 4 a to the fourth, minus a minus, so plus 1 over 4 n to the fourth. Now as a goes to infinity, the 1 over 4a to the fourth goes to 0, and the 1 over 4 n to the fourth is a constant with respect to a, so we get back 1 over 4n to the 4. And we're now ready to kind of tie things together. So what we have is that the error, E sub n, when using the partial sum S sub n to approximate the series, is bounded above by 1 over 4n to the fourth, and we need this to be smaller than 0.001. That is, for what n will this be true? And we now see that we have an equation involving n that we can work with. So if we focus in on this rightmost inequality, what we can do is multiply both sides by 4n to the fourth and divide both sides by 0.001. So if we do that, we would have 1 over 0.004 is less than or equal to n to the fourth. And then we can go ahead and take fourth roots. So the fourth root of 1 over 0.004 is going to be less than or equal to n. And what we have on the left is approximately equal to 3.97. Therefore, our conclusion is that n, because it's a positive whole number, must be greater than or equal to 4. So as a recap, if you see a question that asks you to determine how large n must be in order for the nth partial sum to approximate a series correct to a certain degree of accuracy, if it's something that looks like you could use the integral test, we would like to use the integral test estimation property. You first need to verify that the hypotheses are satisfied, and then once you know they are satisfied, go ahead and apply that inequality.